Hello everyone, please let me know if I am completely audible and visible and my screen is visible to you so that we can start. Anyone, please write in the comment box. Just a yes and no, drop a message. Anyone, please drop a message if I am audible. Okay, so we can start now. So today we are going to do some problems based on the segment trees. We have already seen what is segment tree and why it is used. So let me take you to a precap of the segment trees, and then we'll be starting with the problem solving. Okay, now precap what we have seen earlier. So if you are talking about the precap, so we have seen segment trees. Okay, segment tree is a range query data structure. In segment tree we have like implemented two functions. One is update, another one is query, and like the time complexity of both the functions was log n, where n is the number of elements present in the array. And why the segment tree is used, or what is the use case of the segment trees, or like what was the drawback with the Fenwick trees, so we have used segment trees. So basically segment tree, Fenwick tree is a kind of prefix structure. It stores the result from 0 to a particular index, say x. Okay, but if you talk about the segment trees, in the segment tree if you're talking about the query in range L to R, so basically it dedicatedly stores the result from L to R. Okay, it is not storing it in the prefix based manner, so that's why it is advantageous in this way. Okay, so this is all about the segment trees. Now let us start with today's problem. Okay, so we are starting with the today's problem statement. So what is today's problem statement? Okay, so the problem statement says that a given a array of size n, given a array of size n, and you have to calculate the number of inversion triplets. Okay, so we are given a array having n elements and we have to calculate the number of inversion triplets. Now what do we mean by inversion triplets? Like we have to find a triplets of indices like I, j, comma k, in such a way that where I is like I is less than j and just j is less than k, and ai is greater than aj and it is greater than ak. Okay, so this is our problem statement. We have to find the number of inversion triplets, and this is how the inversion triplets are defined. The triplet of I comma j comma k in such a way that the indices are I less than j, j less than k, and the values are ai is greater than aj and aj is greater than ak. So this is how the inversion triplets is defined, and we have to count the number of inversion triplets. And one thing that we should note, the constraint here is, like, say n can be all the way till 1e5, okay, and you can assume ai to be, say array is a, so ai to be 1e9, and consider all the elements are distinct, all the elements are distinct, okay. So this is the problem statement. So let us try to solve this problem statement with a basic approach. So what could be the basic approach, or say naive, what could be the naive solution for this? So in the naive solution, what you can do, you can nest three loops and three for loops inside, one for the ith index, one for the jth index, and the another one for the kth index, and you can just check the condition, like if ai is greater than aj and if aj is greater than ak, and if this condition holds, then you can increase, like you can initially declare a counter variable and you can just increment that counter, okay. So this could be the very basic approach that you can try, that is the naive solution or a brute force approach. And if you try to compute the time complexity of this one, so for the first loop, for loop, it would go all the way from 0 to n, or say 1 to n, and then for the second loop, the same thing would happen, and then for the third loop, okay. So it would be order of n cube, and it is, we cannot run this in 1 second time, okay. So this is a bad approach, we are not going to use this, we are going to do something good, okay. So now what could be a better approach, what could be a better approach? So if you are talking about the better approach, we can draw some observations from this particular array, okay. Now suppose if you are given an array, if you are given an array and if you are at some particular index, say if this is your particular index, okay. Now what you can do is, like, if this is your middle index, like say j, then I, according to the condition, I should lie in this space, okay, because I should be less than j, okay, and j should be less than k. So according to the condition, I should lie in this space, and the j should lie, like j is this element only, and the k should lie in this space, okay. So k should lie something here and I should lie something at this point, okay, so that this condition holds. And if it is the condition, like I is less than j and j is less than k, if this condition holds, then you have to check the condition for ai greater than aj greater than ak. Now suppose you have fixed your j and you know that this is your jth element, so you would be definitely knowing what is the value of your aj, and then what you just need is how many elements that are that is left to this j and having the value of ai greater than aj. So you have to calculate this number of pairs for this element, and then similarly you can move to the right side, and in the right side you can calculate the same thing, like how many ak are there which is greater than aj, okay. So suppose if you are like, if you are denoting this number of pairs as n1 and if this number of pairs as n2, okay, like you have just found like how many elements are present left to this jth index which is, say, greater than this aj value, okay, and you have denoted it by n1, and then you move to the right space and you have like find how many elements are present in this right part for which the value at that element is greater than the ajth value, and you have marked this n1 and n2. And like suppose if you are choosing any element from n1, like if you are here, we can have a lots of elements in n1, and from this n1 if you are choosing one element and then you are choosing aj, and then from this n2, if you are choosing one element, then this triplets is our desired triplet, then this triplet would be our desired triplet, because in that case I would be less than j and j would be less than k, and ai would be greater than aj and aj would be greater than ak, so the condition holds. So like how many ways we can arrange this thing? So like we can select any value from this n1, and we can like have only one choice for aj, and then we can have n2 choice for this right search space, so that comes out to be n1 into n2. Okay, so this is just for this jth index, say j equals to 3. Now you can move your j all the way from the first index to the last index, and you can do exactly same thing, like for I equals to 0 also, I equals to 1 also, I equals to 2, I equals to 3, all the way to I equals to n. You can just move to the left space and the right space, and you can find this value of n1 and n2, and you are keep adding this n1 and n2, and you will get your solution. So this is your desired result. Okay, now so this is what we have to do, and we have to do it efficiently, because if we are moving a jth pointer, if we are moving a jth pointer, we are doing it in order of n time. Okay, and now we have to efficiently search like uh, how many elements are present from 0 to j minus 1 which are greater than this ajth value. So we have to find it efficiently. Okay, so if by using something, if we find it efficiently, we can solve our problem in a very efficient manner. Okay, so let us look how we are going to do this. So for that, now let us reduce our problem to finding just like at any point, we just need to find, like suppose if I am, my problem is just reduced to query L to R and say X. So this query means we have to find all the elements in range L to R such that the value such that the value is less than X. Not all, find the number of elements. Okay, number of elements. So find the number of elements in range L to R such that their value is less than X. Okay, so this is the sub part of the problem, and if we can efficiently solve this part, we can definitely efficiently solve our problem. Okay, now forget about the problem which we have discussed earlier. We will be coming on that problem later on, but before that we should discuss this particular part. Okay, so how we are going to do this? Now here we are going to use the idea which we have discussed in the earlier lecture, that is segment tree. Now how we can apply the segment tree here? Okay, so by the naive approach, you can just like you can move from L to R and you can just calculate the like if you can move from L to R and you can just keep on checking each element, and if this element is say less than X, you can keep on incrementing your counter, and you can definitely do this by this particular method, and the time complexity for this would be order of n. And suppose if you are given q queries and say q is comparable to n, if q is comparable to n, in that case that would be you will get a time complexity of order of n square, and that is not something we are looking for. Okay, so we are here we are going to use this segment tree and a concept that we have discussed earlier. So now let us look how we are going to do this. Like please write in the comment section if anyone is having any doubts till now. Otherwise I am going to build the segment tree on that particular thing, and we'll be discussing the efficient logic. Okay, so here we are going to use segment trees. So let us consider an example. Suppose we are given an array with 8 elements, and say the elements are 8 comma 7. Mr. Lalit is saying good evening. Okay, good evening. Okay, now 8 7 5 6 2 4 3 1. Okay, I think these are the 8 elements. Okay, so consider this as an example, and now if this is a given array, and suppose we are given q queries, and in each of the query we will be giving you say a value x, and you have to tell like um, how many elements are present in this L to R range which are lesser than this x. Okay, and the given array is this one. So now suppose if we are, say, if we are making a segment tree on this, so let me first draw the segment tree and then I'll be explaining you the logic. Okay, as we have already discussed that the segment tree is a binary tree, so all its nodes would be having at most 2 childs. Okay, so this is what we are doing here. For each node we are just making 2 childs. Okay, okay, so now we can define the range for this one also. Okay, so the range would be like this root node would be storing the result from 1 to 8, this would be from 1 to 4, this is from 5 to 8. Like if you have seen the last lecture, you definitely know what this means. Okay, this is what these ranges means. This is 1 to 2, this is 3 to 4, 5 to 6, and this is 7 to 8, this is 1 to 1, this is 2 to 2, this is 3 to 3, 4 to 4, 5 to 5, 6 to 6, and 8 to 8. Okay, and there would be indices associated with this, so this would be 0 1 2 3 4 5 6 7 8 9 10 11 12 13 and 14. So this is how our segment tree is going to be, and now let us fill some values in this. So what would be the values? So suppose here we will be having 8 because the first index is having a value of 8, then here we are going to have 7, then 5, then 6, then 2, then 4, then 3, and then 1. Okay, now what I am going to do, at every node I am going to like merge these two values in a sorted manner. Okay, and that sorted vector I am going to store at particular node. Okay, so let me do this. So if we like merge it using the logic of merging sorted arrays, then we will be getting 7 comma 8 here, here we will be getting 5 comma 6, here we will be getting 2 comma 4, here we will be getting 1 comma 3. Now suppose if we are merging these two, then we will be getting 5 comma 6 comma 7 comma 8, and here we will be getting 1 comma 2 comma 3 comma 4, and if we merge these two we will be getting 1 comma 2 comma 3 comma 4 comma 5 6 7 and 8. Okay, so these are the values. Now how we are going to answer our query using this particular segment tree? Okay, so now suppose for example if we are like if you are searching from say 2 to 6. Okay, like let me put the indices here. This is 1, this is 2, this is 3 4 5 6 7 and 8. Now for 2 to 6, so this is 2 and this is 6. Now if I am searching for 2 to 6, how many values are lesser in this range is lesser than 6? So how many values in this range is lesser than 6? Is 7 less than 6? No. Is 5 less than 6? Yes. Is 6 less than 6? No. Is 2 less than 6? Yes. Is 4 less than 6? Yes. So these three values are less than 6. Okay, so this should give me output as 3. Okay, because these three values are less than 6, and how we are doing this? By iteratively moving, and that would be going to cost me order of n as a time complexity. Now let me try to use this segment tree which I built over these values, and how we are going to use this to answer that query. Okay, now I can check, like, if I can start from the root node. If this particularly, if this completely lies in my given range 2 to 6, no, this doesn't completely lies, it partially lies. So what we can do, we can move in both the search spaces. So we'll be moving down in both the search spaces, and then in the same way we'll be moving to this search space and this search space, and then from here we are going to move in this particular search space. Okay, now here we can check if this value is lesser than 6. So this value is not lesser than 6, we are not going to calculate from this point. And here we can check this 3 to 4 is completely lying in my query range, so I'll be checking directly, giving my result from this point, this node. So I'll be checking how many values are there in this node which are lesser than 6. So only one. So from here I am getting 0, from here I am getting 1, and then I'll be moving to this search space 5 to 8. So from 5 to 8, as this 5 to 8 doesn't completely lies inside this, but it partially lies, so we'll be moving in both the directions. Okay, and as you can see from here, 7 to 8 is completely outside this range, so we'll be giving the 0 as a result from this particular point. So from this particular point we'll be giving the 0 as a result, and then we'll be checking this 5 to 6. 5 to 6 completely lies inside this range, so we'll be checking the result from this 5 to 6 range. So as both the values are lesser than 6, we'll be giving an output as 2. And here we can, like, if you calculate the sum of all these four values, you will be getting 3 as your result, and this is what the desired result is. So this is how we are going to use our segment tree to answer such type of queries. Okay, now what would be the time complexity? So the worst case would be you have to travel the complete height of the tree, and the complete height of the tree we know is log n. Okay, and now this is log n, and at every node, you know, like at every node you know that the array is sorted, like the vector that is stored at every node is sorted. So here also, here you can, like, run a binary search on that particular vector, and you can find like how many elements are smaller than this one. So for that, a log n factor would be included. So the time complexity for finding in by using the segment tree would be log square n. Okay, and it is, this log square n is much better than this order of n time complexity, so that's why we are using this segment tree. Okay, now what are the different things we are seeing here, like what different things we can observe here in this segment tree, in comparison to the classical segment tree which we have discussed in the earlier lectures. So there we are, at every node we are storing a particular value only, and here you can see that at every node what we are doing, we are storing a vector. Okay, so at every node we are storing a vector. So to implement this kind of segment tree, what we need is a two-dimensional vector. Okay, because at every node we are just storing a vector. Okay, now so this is one different thing we can observe. Now some people might get into confusion, like this is taking order of n square time, as we are, some people can think that we are taking order of n square time because at every node we are storing the vector, and the worst case for the vector to be, like, the vector can be of size n, and that's why we are getting the n square as a space complexity. But this is not the case. If you closely observe here, at this tree, here in this tree, first we are having n elements, and then this n elements is divided into two parts where we are getting n by 2 and n by 2 elements, and this n by 2, each of the n by 2 is divided further into two equal halves, that would be n by 4 and n by 4. Similarly here also you are getting n by 4 and n by 4, and now suppose if you calculate the sum at each level, it comes out to be n only. Okay, so it comes out to be n only, and here if you calculate, it comes out to be n only. and here if you calculate the sum, it comes out to be n only. So like the maximum, what would be the maximum space used by the segment tree? So that would be n times the height of the tree, and that would be n into the height of the tree would be log n base 2. So that's why the space required by this tree is just n log n, not the n square. Okay, so this is one misconception that people might get into. Okay, and we have already discussed the time complexity. Now suppose if you are given q queries, and if you are processing these q types of queries, and the time complexity is log square n, so you would be getting, for q processing q queries, you will be getting q log square n as your time complexity, and if q is comparable to n, you can change it by n, so that would be n into log square n. Okay, so this is all about the time complexity. And now we can implement this particular part. We have already implemented the classical segment tree. Now we are going to implement this particular segment tree. Okay, and like how we can build it? So we will be starting from the root, and then we'll be building the complete tree that we have already discussed in the earlier lecture. Okay, so this is one thing. So first we are going to implement this particular problem, and then we'll be solving our uh, the problem that we have started with. Okay, so any doubts till this point? Anyone having any doubts till this point, please let me know. Otherwise I will be proceeding to the implementation part. Anyone, please write in the comment box. Anyone having any doubts? How we are getting the time complexity, or how we are going to build this segment tree? Any doubts related to this? If you have, please write in the comment box, otherwise we'll implement this. Okay, and like how we are getting, how we are querying on this thing. So we have already seen how we are going to build it, but how we are going to query? So for querying, just we can, like for querying, if you talk about the querying, what we can do for querying? So for querying, we know at each node, at each node the vector is always going to be sorted. Okay, so at each node vector is always sorted. So like vector would be something like this: 1 comma 2 comma say 4 comma 7 comma say 9. So in this manner we are always going to get a sorted vector. So if you want to like search how many elements are lesser than this, say lesser than 5, then what you can do, you can just take the upper bound of this thing, and you can subtract the first value from this, and that the first index from this, and you would be getting the number of elements which are lesser than this one. Okay, so here you can just make use of the binary search functions like upper bound and lower bound to answer your queries on the sorted vectors. Okay, so at each, as each vector is sorted, like at each node a vector is stored and that vector is sorted, so we'll be going to use the binary search on that. Okay, so this is how we are going to do the query. And one more thing that is important here is the shift functions. So I think, like suppose if x is a value, then x into 2 is equivalent to writing x um, left shift 1, and x by 2 is equivalent of writing x right shift 1. Okay, so this is just binary shifting. So I think you must be knowing this. So instead of multiplying 2 and dividing 2, we are going to use this shift functions, because these shift functions are more efficient than this division and the multiplication. And as the segment tree works in the as a order of 4, as a factor of 4, because we are using the 4 into n space, so in that case sometimes we might get TLE. So to get rid of the TLE, we are using the shift function here instead of using the classical division functions. Okay, so now let us implement that particular problem. So this problem is uh, how many elements in the range L to R is lesser than X. So as I am not getting any doubts, I'll be proceeding further to the implementation part. First I'll be including all the header files I need. Okay, then I am defining something. I'll be telling you why I have done this, because I need it. So it is just a shorthand. Okay, like in lot of places I need to write this x dot begin comma x dot end. Like suppose if I am using vector and I am sorting it, I need to write these things. Okay, so instead of writing this, I would be just writing this all x, and that is the meaning of all x is same as this, writing this. Okay, so this is just shorthand, so I have defined a shorthand here. Okay, then I'll be having my main function, and before the main function I'll implement two other functions, that is void build. I'll be building my tree, and at the same time I would be querying something. Okay, these two functions I have to implement. Okay, now in the classical segment tree we have used the 1D array. Here we have to use the 2D array, because every node is storing a vector. There every node is storing a particular value, but here every node is storing a vector. So for that we have to use this, and then we are defining a array, and that array, in this array we will be taking our input. Okay, so in the build we'll be passing three parameters: int start, int end, and int index. So this index is nothing but the index of the node, and the start and end is the left and right limit of their ranges. Okay, suppose if we are building this tree, so at each tree, okay, where is the tree? So here we are having a tree. So in this tree each node has these three variables. One is the starting range and the another one is the ending range, and this particular index. Okay, so we'll be moving from the root, and then we'll be moving all the way till the leaf, and we'll be building a tree. So we'll start from this, then we'll move to this 2 points, then we'll move to those 4 points, and then we'll be moving to these nodes, and from this we are coming back. While coming back we'll be merging them, while coming back we'll be merging them. So this is how, this we are going to do recursively. So here what is the base condition? So the base condition would be when we reach to this leaf, and what is the condition for reaching to the leaf? So the start would be equal to end. Here as you can see that 1 1 1 2 2 3 3, so that would be our base condition in recursion. So if start is equals to end, at that point in this vector we have to insert the value that is provided, okay, that is present at that particular index. So that would be, will be writing this thing. Okay, suppose you can put start here and as well as end also, because both the things are same, as the start and the end value are same. Okay, now after doing this we'll be returning from this particular point. Okay, and if it is not the case, we'll be running this build function for both the left and the right sub half. For that we'll be writing this thing start plus end by 2 that we have discussed. Instead of writing divide by 2, we are just using the shift functions. Okay, and then 2 into index plus 1. Okay, and then we'll be calling the build function for our right subtree. So that would be start plus end by 2 plus 1 till end, and that would be 2 into index plus 2. Okay, and then we have to merge them so that it is sorted in the ascending, say non-decreasing order. Okay, so in the merge function we have to pass the 5 parameters. One is the starting of the first, like the beginning of the first vector and the ending of the first vector, then the beginning of the second vector and the ending of the second vector, and then the vector where you have to put the result. Okay, so for that we are just writing all, that would be writing the beginning and the ending itself. Okay, so what is the, what will be the left part? So the left part would be 2 into index plus 1, and the right part would be 2 into index plus 2. Okay, and then in which vector I have to insert it? In I and index. Okay, so this is all we have to do. So what this line is doing, it is just merging all the two childs, and then it is putting the sorted result in that particular index. So this is what it is doing here in this. Okay, so this will build my tree, and after building I have to query something. So for that I have already made a function. Here I'll be passing the starting range of the segment, the ending range of the segment, the starting of the query, the ending of the query, and the index and the value for which I have to check, like how many elements in this L2R range is lesser than this X value. Okay, so this is what we are checking here, and first we'll be checking the completely lie outside condition. So that would be if, like if L is greater than and or if R is less than S. In that case, what we have to do, in that case, as it is lying outside, so we are not going to get any result from this, so we'll be just returning 0. And if it is a completely lie inside case, so in the completely lie inside case, what would be the condition? So in that case, start should be greater than equals to L, and should be less than equals to R. And if it is the case, we are going to do something, and if it is not, if both of the cases are not true, then we have to go in both the directions, like we have to query in both the directions. So that would be start plus end by 2 comma L comma R, and that would be 2 into index plus 1, and the value of X is going to remain the same, and we are going to like store the result of this query in the left, and then we are going to store the result of the right subhalf in this right variable. So that would be start plus end by 2 comma L by 2, okay, plus 1 till end. L to R is going to be the same, and this would be 2 into index plus 2, and X is going to be the same. Okay, so this is the right part, and then the result would be the sum of this right and this left and right part. Okay, now we have to do something in this part. Okay, so here we know this segment I and D is a vector, and this vector is completely sorted, and in this completely sorted vector we have to tell how many elements in this vector is lesser than this X, is this X value. So what we can do, we can just use the upper bound here. Okay, we can also use the lower bound, because we have to find how many elements which are lesser than this. So for that we have to use the lower bound. So what we'll be doing is, we'll be returning the value of lower bound for all of this segment index. What is the lower bound of this? And this the starting index dot begin. So this will give me how many elements which are lesser than this x value in this particular segment. Okay, so we have implemented our both the functions. If you are having any doubt in the function implementation, like how we are implementing these two functions and what we are doing here, what are these shift functions are doing, okay, and like how we are deciding the condition, if you are having any doubts, please like write in the comment box, otherwise we'll move further. Okay, so here we'll be taking the value of, we'll be declaring a integer variable to store the size of the array. We'll be taking that, we'll be defining, we'll be allocating the memory for our vector. Okay, so here we have taken the input for our array, and then we'll be allocating the memory for our segment tree. Okay, and segment tree is nothing but a two-dimensional vector, so it is something like this, and that would be 4 into n. So we can write it like this, or we can just write simply 4 into n plus 5. Okay, so yes, this is a segment tree, and to store, this is our 2D vector to store the segment tree, and then we can call the build function on this. So the 0 would be starting index and minus 1 would be the ending index, and we'll start from the index 0. Okay, so this is how we are calling the our build function. And after that, what we can do is we can, like, let me check if it is working properly. So yes, we can take our example array, that would be 8 7 5 6 2 4 3 1. Okay, so these are the 4 values and these are the 4 values, so we are having 8 values. Let me check if it is working properly or not. We are getting some errors, let me check. Okay, return 0. Okay, so the return type of the query should be always int, and everything else is, I think, fine. Let me check. Okay, this is also an error. Okay, now I think my segment tree is built properly. Let me check for some query. Okay, so we can check the same 2 to 6, how many elements are lesser than 6, and the result for this is 3. So for that, 0 to n minus 1 would be the base range, and we have to check for the range, what, 2 to 6. So for that we can write 1 to 5, because that is 1 based index, and here we are using the 0 based indexing, and then it should be 0, and what is the value, 6. So it should give me 6 and 3 as a result. Let me check. So we are getting 3. Now let me check for more values, how many elements, like from say 0 to 7 lesser than 6. So this should be 5, because like 1 2 3 4 and this 5 all are lesser than 6. Then for other values we can check, like what are the elements in the range say 1 to 5 which are say lesser than 2. So they should give us 0 as a result, because no, yes, because in this range no element is lesser than 2. Okay, and then you can check how many elements are less in this range is lesser than 9. So it should give 5 as a result, because in this range all the elements are less than 9. Okay, so this function is working properly. Now we have implemented this particular part, and if you like to know what this tree is called, like the tree we have built, this tree is called, in technical terms, this tree is called as merge sort tree. Okay, this particular tree is called merge sort tree. Okay, like in the tree where at every node we are storing the sorted vectors, so this particular tree and this particular segment tree is called as the merge sort tree in the technical terms. Okay, so we are done with this. Now let us come back to our problem. What was our problem statement? In the problem statement we have to find the number of inversion triplets, like I is less than j is less than k, and ai is greater than aj, and aj is greater than ak. So we have to find this inversion counts. Okay, now this inversion triplet we can say. So we have already like discussed the idea. In our idea, what we were doing, we were just fixing our middle point like I, j, k, and this was our conditions. This was our condition, and we are fixing our jth point. Like if this is our array, we are fixing our jth point, and at every point we are checking like how many I are present in this left sub half, in such a way that the ai is greater than aj, and we have assigned n the name n1 to these values, or say the n1 is the number of these values. And then in the same way we have found the k, like in this right subspace how many elements are greater than this, how many AKs are there which are greater than this AJ value. Okay, and we have numbered that as n2, and then n1 into n2 would be our solution. We have already discussed that, and after keep on adding these corresponding pairs we'll be getting our solution. Okay, so we just need two things, like how many in this range, how many elements are lesser than this, and in that range how many elements are greater than this. Okay, so this is now a simple problem. We can implement that problem also, but here we have already implemented this particular function, like how many elements are lesser than this particular value, and we have to just implement for this particular left sub half, like how many elements in a particular range present which is greater than this particular value aj. Okay, so we have already implemented a function for smaller values. We can implement the same kind of function for the larger values. Okay, anyone having any doubt till this point, please write in the comment box, otherwise I will be moving to the implementation part. So we can like say queryless, we can name it as queryless. For this query we can name it as queryless, and like this would be queryless, and we'll be implementing the another function, and that will name as the query more. Okay, so this query will be, this will name it as query more. Okay, and everything would be same, just we have to implement this thing. So that would be like at every point it should be like end minus that. Okay, so yes, this lower bound minus segment index would be the number of elements which are lesser than this one, and if we write like upper bound here, if we write the upper bound here, it would be the number of elements which are lesser than or equals to this particular element, and all the other elements would be greater than this one. So for that what we can do is we can just write segment index dot size, and we can just subtract these values. Okay, so this will give me how many elements are present in that particular range for which the number of elements is lesser than or equals to that particular element, and if we are subtracting this particular count from the complete vector size, so that would be the number of elements which are greater than this one. Okay, so that is what we have done here, and I think now it should work. Okay, so yes, this is query more. Let me check if my query more is working. This is queryless. Let me check for the queryless. Okay, we have done something here. We have to change this name also, so that would be query more, and this thing would be query more. Okay, so yes, this is working fine. Let me check for query more. The answer for this would be 0. There is no element which is greater than this in this particular range, and as we are getting 0 here, let me check for value 6. So this should be only one value. Okay, perfect. Let me check for the complete range 0 to 7. So it should give me 2 as a result, because this 7 and 8, these two values are greater than this 6. Let me check for 0 to 1. This should also give 2. Okay, so my both the functions is working fine, that is the query less and query more. Now I can use this function to write my solution. So what I have to do is I have to just declare a answer variable, and I'll be moving from the first index all the way till the last index. Like we are moving from, okay, we, if this is our array, we are just moving in this search space. Okay, because we need to leave at least one element in the left and in the right sub half. Okay, you can start from this also, but it is better to start from this. Okay, so this is what we are doing here, and now at every point the answer would be the result of query less and the query more. So first the query more. Okay, so the query more would be from 0 to n minus 1, and like what is the querying range? So the query range would be 0 to all the way from to I minus 1. Okay, this range, and so the index is 0, and what is the value for which I have to check? So that is, okay, I should write it as j. So in that case it would be more intuitive to you, because we have understand it in terms of j only. Okay, so because j is the middle element, so we can write it j. So that would be aj. So how many elements which are greater than this left part, which are greater than this aj value? Okay, so this would be calculating this one, and then we can write a query less also. So that would be again from 0 to n minus 1 would be the starting base range, and then what is the querying range? So query range would be j plus 1 all the way to n minus 1, and it is 0, and then aj, like how many elements which are lesser than this one. Okay, so this product we have to add in our solution. Now, okay, let me write this thing for you. Okay, so we can just output this answer. Okay, so we are done with our solution. Let me check for some very simple values. So suppose if 3 1 2 3 is my input array, in that case the answer should be 0. Let me check, it is 0. Let me check for 3 to 1. We are getting 1, because this pair 3 to 1 pair is itself uh, inversion triplet, and let me check for one more thing, like 4, 3, 2 and 1. Okay, let me check how many triplets we are getting with this one. So 4. Now what are these 4 triplets? So can you figure out this thing? So yes, so this is 4, 3, 2, 1. So we can start for this. So 4, 3, 2 would be 1, and 4, 3, 1 would be 1. And if we check for this, so 4, 2, 1 would be 1, and 3, 2, 1 would be 1. Okay, so we are getting the 4 triplets, 4 inversion triplets. So I think our solution is correct and our code is properly working, because if we move further to the bigger inputs, then it is difficult to calculate manually, so we cannot compare an answer, is it? So that's why we have taken these simpler inputs. Okay, so this is, yes, this is all for today's lecture, today's stream. We'll be doing some interesting problems and some interesting topics in the latest series, okay, in the later lectures. Thank you.